Hello and welcome to this new video. In this video, I'm going to solve the exercises of chapter 4. Okay, but before doing this, let me give you some practical rules for the use of the big O notation that I explained in the last video. Okay, we always have xn is a big O of xn, right, by definition. Because recall that big O of xn, so this is not really a number, this is actually a class of functions. So we should really write xn belongs to big O of xn, because big O of xn is any function which is less than a constant times xn at the point where we are dealing, near zero or near infinity or near something. Okay, and when I multiply a big O by a constant, I also get a big O, because constants do not change anything. If I add two big O's or subtract two big O's of the same quantity, I get this big O of the same quantity. When I multiply, powers add, actually, because this is less than a constant times xn, and this is less than another constant times xm. So when you do the product, you get xn times xm. Okay? Now, here, there is a little bit maybe difficult point. We have to precise near which point we are doing these asymptotic estimates. If you are near zero and m is bigger than n, then xm actually is much smaller, is much closer to zero than xn. Okay, so if you like, the ratio is if xm over xn is less than 1. Okay, so a big O of xm is necessarily a big O of xn, but this relation of equality actually is not symmetric. So I cannot just flip them and write big O of xn is big O of xm. It's not really an equality. I'm saying that a function of belonging to this class belongs to this class. So it should be an inclusion relation, actually. For example, take n equal 2, m equal 3. A big O of x3 near 0 is much faster than some quantity that behaves like x squared, because the x cube is much smaller, tends to 0 faster, right? Now, if you are near infinity, the relation changes. So actually, when I say something of the kind big O, this is really something asymptotic. Okay, it's not really a number, right? This is what you should understand, but it's very useful when doing computation, and I will illustrate this on an example. So these are some rules for doing computations. Okay, so at infinity, x cubed is much bigger than x squared. So something that behaves like x squared is, of course, it's less than something behaving like x cubed. So, right? Because recall that x cubed is less than x squared if x is less than 1, but when x is bigger than 1, we have the reverse relation. Okay? Okay, so you will get used to this. Okay? Now, for example, this is an example where we can use these rules to, for example, suppose that I have a quantity that behaves like x plus x squared plus a big O of x cubed raised to the power 2. I want to know like which power of x this quantity behave near 0. Okay, so I have something like a plus b plus c to the square. So we know that this is a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc. So when I do the computation, I get x squared plus x4 plus big O of x cubed, which is big O of x6, plus twice x squared, which is x cubed, x big O of x cubed, and x squared big O of x. There's a 2, but it's not a big deal. Now, this is big O of x6, this is x3, this is big O of x4, and this is big O of x5. Okay? So all these terms actually are big O of x cubed, right? So I can write as x squared plus big O of x cubed. Okay? However, so what do you mean by here? So actually we are just saying that if a function g is of this form, then near 0, the dominating term is x squared. So this function behaves like x squared plus higher order terms. Okay, so this term is negligible in particular, because this is a small o of x squared in particular. So you have to see what are the dominant terms. Now, if you are at infinity, the situation changes because this is actually a big O of x cubed to the square, which is big O of x6. So the denominating term is x6 actually here. Because now at infinity, okay, all these quantities tend to infinity at infinity, but a big O of x cubed is much bigger than these two. So I can neglect these two at infinity. Okay. Okay, now let us start by solving the exercises. We have to prove some very familiar and known Taylor series expansions near zero. The exponential, you may know it. So it's 1 plus x over 1 factorial plus etc. plus xn over n factorial plus the big O of xn plus 1. Len of 1 plus x near 0 can be written as x minus x squared over 2 plus etc. So the general term is minus 1 and minus 1 xn over n, plus a remainder which behaves like xn plus 1. And we have these formulas for sine and cosine. And this may be new, 1 plus x to the 1 half. This is radical of 1 plus x. Okay. So what we are doing here is we are approximating these known functions by polynomials of arbitrary order, because n is arbitrary here, actually. So we just apply Taylor-Cauchy or Taylor-Young if you like, same thing. If f of x is ex, then all the derivative of f is the same. It's just ex. So the derivatives at 0 is 1. So just apply Taylor-Cauchy, right? Because this is 1 over n factorial, the general term. And don't forget to divide by the factorial of the quantity. Okay? So this is easy. Now for the second one, if f is len of 1 plus x, then when I differentiate one time, I get 1 plus x to the minus 1. And so at 0, we have 1. If we differentiate another time, I put it explicitly in this way because it's now easier to differentiate. So because this is a power now, so it's minus 1 times 1 plus x times minus 1 minus 1. So the second derivative at 0 is minus 1. When I differentiate another time, I get minus 1 times minus 2 times 1 plus x to the power minus 2 minus 1, so minus 3. So we get 2. At 0, we get 2 or 2 factorial. If I differentiate another time, I get minus 3 times 2, which is minus 3 factorial, times 1 plus x to the minus 4. So at 0, get minus 3 factorial. And one more time. So now I hope that you are seeing a pattern here. So what is the pattern? In general, fn at order 0 is minus 1 to the n minus 1, which is either plus or minus 1, okay, times the factorial of n minus 1. Okay, you can prove this by induction if you like. If you are not convinced, actually, but you need a formula for this. So the formula is fn of x is n minus 1 factorial times minus 1 to the n minus 1 times 1 plus x to the power minus n. Right? So you can prove it by induction if you like. Okay, and now we just apply Taylor-Cauchy, right? And that's it actually. So, but when we divide over the n factorial, we get minus 1 to the n minus 1 over n, because the factorial simplify. Okay, so this is why we get this plus or minus over n. Now for the sine, it's very easy. When we differentiate one time, we get cosine, so at 0 we have 1. Another time minus sine, so at 0 it's 0. Third time minus cosine, so minus 1. Fourth time sine x, so 0. And we repeat again. So this is the sequence actually at 0 is 1, 0, minus 1, 0, 1, etc. So it's periodic of period 4. Okay, and that's it. So in general, when the order of the derivation is odd, we get minus 1 to the n. And when it's even, it's 0. Okay, so just apply Taylor-Cauchy, but so we divide. Here we must divide by 2n plus 1 factorial. Here it's just 0. Okay, and we get the formula. So it's very easy. Now for cosine, it's similar, but also we have a periodic of period 4, but the order changed. So the first derivative is minus 0 actually. So I have 0, 1. Okay, so right. So you do it. Okay, last example, radical of 1 plus x. Okay, we do the same. We differentiate one time. We get 1/2 1 plus x to the power minus 1/2. So at 0 we have 1/2. Another time we get 1/2 times minus 1/2. Okay, so at 0 it's minus 1/4. And we have to divide by 2 factorial. So this is why we get 1/8. A third time we multiply the previous number by 3/2 actually. Okay, so but 3/2 can be written as 1/2 minus 2. So we see the pattern here. If I differentiate another time, I get 3a/8, the previous one multiplied by minus 5/2, and I can write minus 5/2 as 1/2 minus 3. So this is the pattern: 1/2 minus 0, 1/2 minus 1, 1/2 minus 2, 1/2 minus 3. Right? And I should divide by 4 factorial now. So this guy is n minus 1. So it's easy now to see that the general term is 1/2, etc. up to, so each time I subtract a bigger integer, an integer plus 1, up to n minus 1. So from 0 to n minus 1. So there are n terms actually here. And we divide by n factorial, and that's it. Okay, so this concludes the first exercise. Second exercise, we have to approximate sine of 0, 1 in radian, of course. So 1 radian over 10 without a computer, actually, just by paper and pen. So, and this is actually how computer compute the sine, by using a power series expansion. So we write Taylor-Lagrange to order 4, excuse me. Okay, so the remainder is something of x5. Okay, here there's no x4 because the derivative of sine at the fourth time is sine. So at 0 it's 0. Okay, so this is the Taylor-Lagrange formula of order 4, right? So the remainder is, of course, I can write sine c x4 over 4 factorial, but this is better actually. Okay, in your book they stopped at 4, but actually this is a better approximation, right? Because this is Taylor-Lagrange up to order 4. So the Taylor polynomial at near 0 of sine x has order 3, okay, because there's no power of 4. And so now, in particular, if I replace x by 0, 1, I can approximate the sine of 0, 1 by this Taylor polynomial at 0, 1, and I can compute it actually very easily. And you should get 0.0998333. Okay, and now the question is, how good is this approximation? Well, I can estimate the error, because this is the error committed. Now, I don't know the error precisely because I don't know C, but I can do an estimate of the error. So the error in absolute value is cosine C times 0, 1 to the 5 over 5 factorial. I don't know C, so I don't know the error. But since cosine is less than 1 in absolute value, the error is less than 0, 1 to the 5 over 120. And this is 8.33 10 to the power minus 8. So at any rate, it's less than 10 to the power minus 7. So what does this mean? It means that it's a very good approximation. The error is very small. So it means in particular that the 7 first digits of sine are correct. 1, 2, 3, 4, 5, 6, 7. So these are correct actually. So this gives you an idea of how we can use the Taylor approximations to compute sines and cosines. Okay, third exercise, compute the limit. So here we have usually two options. Either we use the L'Hopital rule, or we use a kind of Taylor formula, usually Taylor-Lagrange or Taylor-Young or Taylor. Okay. So let us start with the first one, ln of 1 plus x over radical x. If I use L'Hopital rule, of course, because I have something of the form 0 over 0, because ln of 1 plus 0 is 0. So when I differentiate, I get 1 over 1 plus x over this. I don't need to differentiate another time, but I just rearrange this by writing 2 radical x over 1 plus x, and this is easily seen to tend to 0, because just replace x by 0. Okay? Now, the second method is to use exercise 1. So we write Taylor polynomial up to order 1, actually. So this is a linear approximation of ln of 1 plus x. Right? So here I'm approximating ln of 1 plus x by a line. Okay? And by the way, this is the tangent to the graph. So when I divide by radical x, okay, here, well, we get x squared over radical x, so it's x 3/2. And when x tends to 0, this tends to 0. So actually, I have a precision actually here. So I know, I prefer this method. Why? Because it not only gives me the limit, but it gives me the behavior of the function near the point. So I know that this function near 0 behaves like radical x plus higher order terms. Okay? So this is more precise because the limit can be 0, but near 0, how do you behave? Do you behave like x squared or x cubed or sine x? How do you behave? This is more precise, actually. Okay. Now, second one, 1 minus x over tangent x. I can use L'Hopital rule, which is very easy here. So when I differentiate, I get sine over the derivative of tangent can be written in two ways, either 1 plus tangent square or 1 over cosine square, because it's the same thing. And now we easily see that it's 0. Now here, if we can use, of course, the Taylor expansions, but it involves more computation because we have to find the Taylor approximation of tangent. It's doable actually, and when you do it, you get a more precise result actually. You try to do it. Try to expand tangent x near 0 just up to order 3. It's enough. Okay. So just compute the first, second, third derivative, or just second derivative is okay actually, right? So try to do it as an exercise. But here, of course, the limit is simpler. Third limit is easy by L'Hopital, x over 1 plus xn minus 1. So it's easily done. Just differentiate, and we get 1 over n. Okay, now for the fourth one, x squared minus sine squared x over x squared sine squared. Okay, this is a little bit heavy in computation, but you should be able to do it. Okay, so I will present the two methods. Okay, and you choose the one you like. But once again, the second method, which is Taylor approximation, is more precise. Okay, how do I do the computations? The derivative of sine squared is 2 sine cosine, so it's sine to x. Okay, so this will simplify my computations. So of course, I have something of the form 0 over 0. And if you want to be rigorous, you need to check that the denominator vanishes only near 0. Okay, but how do you know this? This is easy here because sine squared near 0 sine x behaves like x, so this behaves like x4, right? So when I differentiate, I get 2x minus sine 2x over the derivative of x squared times sine squared plus x squared times the derivative of sine squared. So this is the product rule. Now, once again, if we want to apply L'Hopital rule, we need to check that this is this does not vanish, or just vanishes only at 0. But this is easy to justify because I have something of the form x cubed, so this is a big O of x cubed, right? Anyway, so this is still of the form 0 over 0, so I differentiate another time, and I get 2 minus, now sine 2x, the derivative of sine is cosine, so it's, by the chain rule, it's minus 2 cosine 2x. And here I apply the product rule, so the derivative of x is 1, so 2 sine squared, plus 2x, the derivative of sine squared, which is sine 2x. Now this term, the derivative of x squared is 2x, and so on. Now we still have something of the form 0 over 0. So we differentiate another time. So we get 1 minus, so just first I simplify by 2, right? So because here I have 2x sine 2x, 2x sine 2, so this is 4x. And when I simplify by 2, I get 1 minus cosine 2x, sine squared plus 2x sine 2x plus x squared cosine 2x. Okay, so this is still of the form 0 over 0. So I differentiate another time, and I get 2 sine 2x over this. Now, of course, I can simplify here because this is 3 sine 2x and this is 6x, right? So I simplified. And now we could apply another time L'Hopital rule, but it's not necessary because when we divide by sine 2x, numerator and denominator, what do we get? We get 3 here and 6x over sine 2x, cosine 2x, minus 2x squared. Now, why I wrote 6 3 times 2? Because now 2x over sine 2x tends to 1 as x tends to 0. Right? And this is 1. So the numerator tends to 2, the denominator tends to 3 plus 3, which is 6. So it's 1/3. Okay. Not terribly difficult, but just have to be patient. Okay, now the second method, Taylor approximation with the big O notation. So I know that sine x, yeah. Sorry, there's an error here. Actually, it's just next. Yeah. I think there's an error here. It should be x to the 5. I'll correct that. Yeah, so there was just a small error. I put here x6 instead of x5, but the result is correct. Because now, as we did at the beginning of the video, we just raised this sum to the power 2. So we get x squared. This is then a term of order x6. This is a term of order x10. Now plus or minus actually twice x times this. So this gives me minus x4 over 3. So this is the term of order 4. And then we have higher order terms. So we have x times big O is big O of x6. This is big O of x8. And that's it actually. So we can write this sine squared as x squared minus x4 over 3 plus a big O of x6. Okay? So, and now we replace, right? In the numerator, we get x squared minus this quantity. So the sine squared behaves like x squared minus x4 over 3 near 0. So we simplify and we get x4 over 3 plus a big O of x6. The denominator, we just do the multiplication, just x4, x6. So it's x4 plus big O of x6. When I divide by x4, I get 1/3 plus big O of x squared over 1 plus big O of x squared. And when x tends to 0, this tends to 0, this tends to 0, and we get 1/3. Yeah. I usually prefer this method, actually, because it's more precise. And it seems a little bit simpler, actually, but you just have to get used to this notation. Okay, so final limit. Okay, so it's tangent x over tangent 3x as x tends to pi over 2. Actually, I put pi over 2 minus, so it's the limit from the left. but it's not really important because the limit from the right is the same actually. So just to simplify my computation, the derivative of cosine square ax, if a is a constant, if you do that by the chain rule, it's 2 cosine x times minus sine x times a. So it's a times sine 2ax. Okay, now I apply L'Hopital rule. The derivative of tangent, I write it as 1 over cosine square. And by the chain rule, the derivative of the denominator is 3 over cosine square 3x. Now I rearrange that. So it's cosine square 3x over 3 cosine square. And now, of course, this is some of the form infinity over infinity here again as well. But we know that L'Hopital rule, we can use L'Hopital rule if I have something of the form infinity over infinity. So I differentiate. Now I use L'Hopital rule to this. The derivative of cosine squared 3x, according to what you said, is minus 3 sine 6x. And same thing here, because the derivative of cosine squared is sine 2x. And the 3 comes from here. And now I simplify by minus 3. And I differentiate again. I use L'Hopital rule again. So the derivative of sine 6x is 6 cosine 6x. And sine 2x, the derivative is 2 cosine 2x. So I get 3. And now this is not indeterminate actually, because when I replace x by pi over 2, I get cosine 3 pi, which is minus 1. And when I replace 2x by pi over 2 here, you get cosine pi, which is also minus 1. So 3 minus 1 over minus 1, which is 3. Okay, so this concludes the third exercise. Fourth exercise, just an exercise to illustrate the use of Taylor polynomials in order to determine the position of the graph with respect to its tangent and to determine the inflection points. Okay. Now, of course, I took a polynomial here. So when I do the Taylor approximation, I can get an exact actually, because this is a polynomial. So if I want to, I can write this polynomial as power in powers of x minus 1/2. And I still get a polynomial of order 4 actually. But this is not necessary. So now we want to find the tangent near 1/2. So we can, of course, one way that you may know is to write x minus 1/2 plus 1/2 to the 4 and then expand. And here do the same thing. This is one way. It's not a problem. Or you can do the Taylor approximation up to order 3 if you like. Or 2 is enough actually. So you just compute the derivative and evaluate it at 1/2, you get minus 1. And the second derivative evaluated at 1/2 is minus 3. So, and just have to divide by 2 factorial, right? Yeah, so, and if you differentiate another time, you get 24x minus 12. And if you differentiate a fourth time, you get 24, and then you get 0 actually. Okay, so if you apply the Taylor-Cauchy formula near 1/2, we get f of 0 plus f of 1/2, excuse me, f of 1/2 plus f prime of 1/2 divided by 1 factorial times x minus 1/2 plus f double prime at 1/2 over 2 factorial times the square plus a remainder of order 3. Okay. We can compute it explicitly if you like, okay, but it's not necessary. What is really important here, because this method is generalizable actually to other functions. So this is the equation of the tangent here. So this is, if you like, the linear part of f. Now, if I do the difference, f minus its tangent, we get this. The dominant term in the remainder is minus 3/2 x minus 1/2 squared. And this is something negative because this is negligible actually. You can write it as small o if you like. It's not really a big deal. So you can use Taylor-Young if you like. It's enough. Taylor-Young is enough here. So this term is negligible near 1 with respect to this term. So this is the dominant term, and it has a negative sign. So locally, near 1/2, f is below its tangent at 1/2. And in your book, actually, they drew the graph and the tangent, so you can see the picture. Or you can use a software to plot the graph, or you can plot it by yourself if you like. So this is, I just want to illustrate how the use of Taylor formulas can be, at least to order 2, can be very helpful in determining the position of f with respect to its tangent. Okay. Now, second question, find the inflection point. Now, what is an inflection point? An inflection point is a point where the graph crosses its tangent, right? So we have a change of convexity, if you like. And we can prove, and you maybe proved it in school, that at an inflection point, the second derivative is 0. So inflection point implies it's a 0 of f double prime, but the converse is not true, right? Because if you take f of x equal x4, the second derivative at 0 is 0, but 0 is not an inflection point because the graph of x4 is just above the tangent, okay? So if you want to find the inflection point, you have to find them among the zeros of f double prime. So here, we already compute f double prime. So when you solve the equation f double prime equals 0, we get x squared minus x equals 0. So x equals 0 or x equals 1, because I can factor by x here. So it's x minus 1. So let us look at what happened near 0. At near 0, I don't need to find any Taylor polynomial because it's already given, right? So because f is already a polynomial. So this is the, if you like, the Taylor expansion of the polynomial itself. So I don't have any remainder here. So now the tangent, but of course here, the tangent is 0 because f prime is 0 at 0, right? So it's a horizontal tangent here. So when I look at the sign of f of x minus its tangent, right, I get minus 2x2 plus x4. So what does this mean? It means that, so of course this is dominant. This near 0, this is the dominant term. This is negligible, right? So if x is negative, this quantity is positive. And when x becomes positive, it becomes negative. So we have a sign change near x equals 0. So this precisely means that 0 is an inflection point, okay? Because when x is negative, f is above the tangent, the horizontal tangent in this case, okay? And when x is positive, it's below, okay? And you can see the picture in your book. Okay, now for the other inflection point 1/2, well, we don't know if it's an inflection point, but we shall see that this is the case. Okay, so we just write f. So we have two ways here actually. I already told you that you can take f and instead of x you write x minus 1/2 plus 1/2 and you expand. This is one way, so you get this. Or you just compute the Taylor approximation, the Taylor polynomial of f, which should be exactly a polynomial of order 4 and with no remainder. Okay. So it happens that in this case, because f is a polynomial, there is no remainder. So this is exact here. So now the tangent actually is minus 2x minus 1. Okay, so when I do the difference of f of x minus its tangent is 2x minus 1 cubed. So this is a cubic term. So when x is less than 1, it's negative, and when x is bigger than 1, it's positive. So I also have a sign change, right? So this means that x equal 1, at x equal 1, I have an inflection point. And you see the picture in your book, right? So it's not always this case, but here this is just to illustrate. If I had a term of order 4 here, for example, then this is no longer an inflection point because it doesn't change sign, it has constant sign. However, if I had an odd power, and this is the purpose of the exercise, if I had an odd power of x minus 1, then it would be an inflection point, right? So odd power inflection point, when I just do the difference between f and its tangent, is if it's an even power, it's not an inflection point. Okay, so this concludes the exercises, and the course as well. So congratulations, you finished the course. So I wish you good luck in your exams. So it will not be difficult, of course, because we know the situation is difficult now for all of us. But you should study a little bit at least. Okay, so you don't expect to have hundreds actually if you don't study. Okay, so thank you for your attention. Good luck in your exams, and see you soon if you like.